Okay, so in the last class we discussed about the oxidation states, right?
Yes.
So these are some rules for the oxidation states. And then I have asked you to learn this table that there are some elements which shows the usual oxidation state in some of its compounds, which you have to remember. Have you learned it?
Yes, I think I have. But not everything so far.
So there are two more rules for writing the oxidation states. Okay, so first rule is that atoms of transition elements, they can have variable oxidation states in their compounds. Transition elements means they are d block elements which lies in the middle of the periodic table. For example, iron is a transition element, copper is a transition element, manganese, chromium. Okay, iron, the symbol for iron is Fe. For copper it is Cu. For manganese it is Mn, and for chromium it is Cr. So they show some common oxidation states. They show some variable oxidation states. Like iron can show +2 also, +3 also. Copper can show +1 and +2. And manganese can show +2 also, +4 also, and +7 also. Okay. So here, when you write down the name of the compounds like iron chloride, so the oxidation state, it should be included in the bracket. For example, in iron chloride, it is mentioned here that iron should be in the +3 oxidation state. Similarly, for copper oxide, copper shows +1 and +2. So how do we know that which copper we are talking about? So we write the oxidation state in brackets in the transition elements which shows more than one oxidation state. So this is the fifth rule. Sixth rule says that in any formula, the oxidation states must add up to 0. Okay. For example, let us see magnesium chloride. Magnesium chloride. Now, what is the oxidation state for magnesium?
Sorry.
What is the oxidation state for magnesium? Look at the table and then tell me.
Numeral values.
Yes, for magnesium, what is the which group does it belong? Look at the table here. It belongs to which group? Magnesium. It belongs to group 2, right?
Yes.
So what should be the oxidation state for magnesium?
+2.
Yes. So you have to write here how to write down the oxidation state +2 for magnesium. Okay. And the chlorine. What is the oxidation state for chlorine? Look at the table again. Tell me the oxidation state for chlorine.
-1.
Yes, it is -1. So there are two chlorine atoms. Two chlorine atoms. So you have to multiply 2 with the -1. It becomes -2. So you can see here that +2 and -2, they add up to 0. So in any formula, the oxidation state, it must add up to 0 if it is a neutral compound. For example, magnesium chloride, it is MgCl2 only. Okay, there is no charge on magnesium chloride. That means the charge on magnesium, the oxidation state of magnesium, it cancels out the oxidation state for chlorine. Okay, is it clear this slide?
Yes.
We'll take a screenshot of this. Write this before the next class.
I've taken.
Okay, so here also you can see that they all are copper. Like A is my copper metal, but B is my copper chloride, C is also copper chloride, but it is green in color and it is blue in color. So what is the difference between them? So in first part, copper is present in +1 oxidation state, and in the C part, the copper is present in the +2 oxidation state. So you can see that oxidation state, how oxidation state can differ and how the compounds can differ from the differing oxidation states. If it is in +1, then the compound is green, and if it is in +2, then it is blue. And if it is neutral copper metal, then it is brown in color. Okay.
Yes. Done.
Now oxidation states change during a redox reaction. Okay, so as I told you that redox reaction is a reaction where reduction and oxidation, both processes take place simultaneously. Both processes takes place together. It is called a redox reaction. Now if you want to write down the oxidation state for sodium, what it should be? It should be 0. Why? Why it should be 0? Because of these rules. What is the rule here? Look at the fourth rule, that many elements, look at the third rule, that where an element is not combined with other elements, if it is alone, it is not combined with any other elements, its atoms are in oxidation state 0. So here sodium is not combined with anything, so its oxidation state is 0. It is in the elemental form. Chlorine also, it exists as a gas. It is also in the elemental form. Its oxidation state is also 0. And if you want to write down the oxidation state for chlorine in NaCl, then you know it is -1. Chlorine is -1 from that table. If it is -1, then sodium should be +1, because +1 -1, they add up to 0. So each sodium atom loses an electron during the reaction to form Na+ ion. Okay, many times we discussed this, that how sodium atom is losing its outer valence electron to form Na+ ion. If it is losing the electron, so sodium is oxidized, right? Because oxidation is loss of electron. And you can see that oxidation state of sodium, it rises from 0 to +1. So if oxidation state increases, it is oxidation. This is your fourth definition. And if oxidation state decreases, it is your reduction process. Okay. So each chlorine atom, chlorine will gain an electron and it forms a Cl- ion. So you see, if chlorine is going from 0 to -1, that means decrease in oxidation state is happening. Okay, and decrease in oxidation state is reduction. So we say that chlorine is reduced whereas sodium is oxidized. Is it clear how to identify the oxidation and reduction? If you are given a chemical reaction and you know its oxidation states.
Done.
So if oxidation states change during a reaction, it is a redox reaction. So this is also a definition of redox reaction, that if any reaction oxidation state is changing, then it is a redox reaction. Changing means it should increase and it should decrease. For example, if it is going from 0 to +1, +2, +3, +4, then what happens? It is the rise in oxidation number. That means oxidation has occurred. And if it moves from here, from 0 to -1, -2, -3, -4, so this we can see it is the fall in oxidation number. So it means reduction has occurred. Okay.
Yeah.
Hey students! Interested in boosting your studies? Enroll now at Keddy Edtech. We offer online tuition for the Cambridge curriculum, grades 6 to IGCSE, AS, and A-level. Start learning with us today.
Done.
So now we are using the oxidation states to identify the redox reactions. Okay, so we are going to see 3 examples. In example 1, iron reacts with sulfur to form iron sulfide. which is the symbol for iron. You should know the symbols. For sulfur, it is S, and it forms iron 2 sulfide. That means oxidation state for iron is 2. If it is 2 for iron, then sulfur should be -2. Why? Because +2 -2 is equal to 0. Fe is in the elemental form, it is 0. Sulfur is also alone, and in the elemental form, it is also 0. Now you can see here that iron is moving from 0 to +2, that means oxidation, and sulfur is moving from 0 to -2, decrease in oxidation state, that means it is reduction. So both the processes are happening, so it is a redox reaction. In example 2, when chlorine is bubbled through a solution of iron chloride, so this is FeCl2, okay, this is your FeCl2. The oxidation state for iron here is 2. It is written here, it is 2. And the chlorine, we know it is -1. Chlorine is in the elemental form here alone, it is 0. FeCl3, here it is given that iron is in +3. Chlorine, we know it is in the -1 oxidation state. Now there also the change in oxidation state is occurring. Iron is moving from +2 to +3. And chlorine is moving from 0 to -1. So increase and decrease in oxidation state is happening. So it is a redox reaction. In example 3, ammonia reacts with hydrogen chloride. It forms ammonium chloride. So you should know the oxidation states. For nitrogen, it is -3. For hydrogen, it is +1. Okay. Similarly, for chlorine, it is -1. Now in NH4Cl, you should know the oxidation states. Here, see, nitrogen is in -3, and here also nitrogen is in -3 oxidation state. So no change is happening. Hydrogen is in +1, hydrogen is in +1. No change is happening here also. So there has been no change in oxidation state in this reaction. So we can say that this is not a redox reaction. So you can easily identify redox reactions using oxidation states. If oxidation number is changing, if it is increasing and decreasing, then it is a redox reaction. And if it is not changing, if it is same in reactant side and product side, then it is not a redox reaction. Is it clear? So please take a screenshot of this slide and once read this slide on your own.
Okay. Done.
So this is your homework question for today. Write a word equation for this reaction. Okay, so take a screenshot for this. You have to just tell which substance is oxidized and which is reduced. So read it once and then take a screenshot. Now we are going to learn about oxidizing agent and the reducing agent. So it is also very simple. If you understood what which substance is oxidized, which substance is reduced, then you just have to do the opposite. The substance which is reduced, it is the oxidizing agent, and the substance which is oxidized, it is the reducing agent. You just have to reverse it. The oxidizing agent, it oxidizes another substance, but itself it is getting reduced. Similarly, reducing agent, it reduces another substance. That means it is a helper. Agent basically it means a helper, right? Agents. So reducing agent, it reduces another substance while itself it gets oxidized. So let us see the reaction of copper oxide, that is CuO plus hydrogen to give copper and water. Now here you can see that copper oxide is converting to copper, removal of oxygen, right? Removal of oxygen is reduction, and the substance which is reduced is known as your oxidizing agent. So copper oxide is known as your oxidizing agent. Similarly, hydrogen is converting to water. That means addition of oxygen, right? Addition of oxygen is oxidation. That means it is oxidized. And the substance which is oxidized is known as your reducing agent. So H2 hydrogen is your reducing agent here, and copper oxide is your oxidizing agent. Is it clear the difference between oxidizing agent and reducing agent? Am I audible?
Sorry, I thought I was unmuted. I said yes.
Okay, so please read it once, the entire slide, and then take a screenshot. If there's any doubt, please ask.
Okay. Done.
Okay. Now, another point to note is that oxidizing agents are sometimes also called as oxidants, and reducing agents are also called as reductants. So, if in the question it is asked that identify oxidant, so it means oxidizing agent. Oxidizing agent means the substance which is reduced. If the question says that you have to identify the reductant, so you have to understand that reductant and reducing agent is one and the same thing. Reducing agents are those substances which are oxidized itself. Okay.
Yeah. Done.
Okay. Now in the laboratory, there are some oxidizing and reducing agents we use. Some substances have a strong drive to gain electrons. Okay. So that means gain electrons means reduction. Reduction is gain of electrons. Reduction means they are acting as oxidizing agents. Okay. So some substances have a strong drive to gain electrons, so they are strong oxidizing agents. Oxidizing agents means they oxidize other substance by taking electrons from them. Examples are your oxygen and chlorine. Oxygen and chlorine are your oxidizing agents. While some substances are strong reducing agents, they give up electrons to other substances. For example, hydrogen, carbon monoxide, CO, okay, and metals like sodium, they act as your strong reducing agents. Okay, so in the laboratory, some strong oxidizing agents are oxygen and chlorine, and reducing agents are hydrogen, carbon monoxide, and sodium. Now, how to identify them? Because we have to identify them. So they, the oxidizing and reducing agents, they show a color change when they react. So this makes them useful in lab tests. We will study first one, that is potassium permanganate. First of all, read this and take a screenshot. Oxidizing and reducing agents in the lab.
Okay.
Done.
Yes.
Okay. So first one is your potassium manganate. Potassium manganate, we use it in our lab. Its formula is KMNO4. This 7 is the oxidation state of manganese. Okay. It is a transition element. This is manganese. It is a transition element. So as I told you in rule number 5, that transition elements can show various oxidation state. So it can also show various oxidation state. It is a purple colored compound. Okay. So in it, the oxidation state of manganese, how you can calculate is, first of all, you have to write down the oxidation state for potassium. It is +1 because it belongs to group 1 and all the group 1 metals have oxidation state of +1. Plus manganese you don't know, so let it be X. Plus there are 4 atoms of oxygen. The oxidation number of oxygen, you know it is -2 is equal to 0. So simple maths, when you solve it, you get x plus 1 minus 8 is equal to 0. Then you get x is equal to 7. That means oxidation state for manganese is 7 plus 7. But it is much more stable in oxidation state +2. So what happens? It is strongly driven to reduce its oxidation state to +2 by gaining electrons. If it gains 5 electrons, then its oxidation state is reduced to +2. That's why potassium manganate, it acts as a powerful oxidizing agent. It takes electrons from other substances in the presence of a little acid. That means in the acidic medium, manganese in +7 oxidation state, it gets converted to manganese in +2 oxidation state in the acidic medium. Okay. So it is itself reduced in the reaction because oxidation state is decreasing, right? And if oxidation state decreases, then it is reduced. So it decreases with a color change like this. So take a screenshot of this slide. So here this is your purple color. When it reduces to manganese plus 2, it becomes colorless. So it can be used to test for the presence of a reducing agent. If a reducing agent is present, purple color will fade. So this is a test to test the presence of a reducing agent. If there is no reducing agent, the purple color will remain as it is. But if there is a reducing agent means which reduces other substances and itself it gets oxidized. Okay. So let's end the session here only. In the next class, we are going to learn the next reaction, that is potassium dichromate, which we use in the lab.